All right, with Newton's laws in motion, there's really nothing new in this section other than stuff that we've done. It's just kind of putting things together. So we've spent a little while um, talking about this F equals ma. So this equation over here, Newton's second law. Previous to this unit, we had talked in kinematics. There was a whole bunch of different kinematics equations, right? The big five equations. There's a bunch of them. This is just one of them, but there's a bunch of them. And the question kind of comes up, what do these things have in common? It's that acceleration. So if you're given information like things to do with force and mass, you could solve for acceleration using Newton's second law. If, on the other hand, you were given some velocities and a time or a displacement or something like that, then you could solve for acceleration using kinematics. In this section, what we're going to have to do is use either kinematics, solve for acceleration, and then use it, like plug it in over here to solve for one of the forces maybe. Or on the other hand, I could give you a force and mass. You solve for acceleration over here, and then use it over here to solve for V2 or something like that. Okay, so let's do a question like that, and we can kind of see what this thing looks like. Let's say the Millennium Falcon has a mass of 22,000 kilograms. I don't know what it really is. I mean, of course it's fake, but anyways, Han Solo says, punch it, Chewie. The ship generates a bunch of force forwards. The force acts for 10 seconds. The ship starts from rest. What's its final speed? And then eventually, what distance does it cover during this time? So let's write down what we know. What we've got is a mass. The mass of this ship is 22,000 kilograms. We've got a force. Okay, so I would call this like an applied force. 1.47, that's a point there, 1.47 times 10 to the 8 newtons. Then we've also got a time. We know that the ship starts from rest. What's its final speed? We've got a bunch of like force information. So if you think of F equals ma, okay, we've got a bunch of information that can go into that. And then if you think of kinematics equations, let's say kinematics over here, kinematics. I got to remember how to spell that thing. We've got some other information. We've got time is 10 seconds. We've got V1. It starts from rest. V1 is 0. What we're looking for, let's just worry about A for now. What we're looking for here is what's V2. Remember, we talked about this when we talked about kinematics. We always mentioned that you need 3 pieces of information. We don't have 3. We've only got 2 pieces of information. What that means is we're going to have to start over here in our force information, mass and force and stuff like that. We're going to have to solve for acceleration. Okay, so over here, acceleration is question mark. But once I know this acceleration, then I'm going to sub that in over here to this. Okay, so this thing and this thing are the same. So my method to solving this thing then is use this information over in force land, solve for acceleration, plug it in over here into kinematics stuff, then I can solve for V2. Okay, if I was to draw a quick little free body diagram, I don't know which way this thing is going. Let's just imagine it's going this way. So there's an applied force. We're out in space. That's supposed to say FA there. We're out in space, right? There are long ways from any planets or Death Stars, or I forget what all that stuff is in Star Wars, but there's an applied force here acting. That's it. There's no friction in space. There's no gravity from nearby planets. We're a long ways from anything. This is our net force. Okay, so if I say sum of F equals ma, it's really applied force equals ma, because that's the only force there is. You could write this if you wanted. You could write it as what we're often used to seeing is like FA minus FF, but FF is 0. Okay, so the applied force, 1.47 times 10 to the 8. The mass, where was that up here? 22,000 times acceleration. We divide both sides by 22,000. Acceleration, let's see, I did that somewhere. 6681.8, it looks like. Can't read my own writing. 66818 No, 6681.8. 6681.8. Brother, I should have just done it on a calculator. Would have been quicker. You could say forwards here to make this into an acceleration, a good acceleration. That's going to go in here as well. 6681.8. That's meters per second squared forwards. Now we can use kinematics information. Okay, so now I could use this guy, for example. We're looking for V2. V1 is 0. This number, 6681.8, times a time of 10 seconds. V2, 66818 meters per second. Again, forwards for velocity. They just ask for speed. Okay, so we could say with sig digs, I guess it's 2 sig digs because of this number. Now, if we pretend there's a decimal at the end, let's take it as 3 sig digs. Okay, so we're going to say 66.8 kilometers per second, or you could say 66.8 times 10 to the 3 meters per second forwards. And again, we're pretending there's a decimal at the end of this, so we'll take that as 5 sig digs. Okay, so there's A, all that part. Let's see if I can squeeze B right over here. What distance does it cover? Well, we're actually going to find displacement. We'll pull out the best friend equation because we always seem to use this guy. V1 is still just 0. Okay, so 1/2 times acceleration. What was that? 6681.8 times time squared. We sub into there and crunch out some numbers, and we're going to get 334, what is that, 090 meters. Again, for 3 sig digs, so we could say approximately 334 kilometers, or 334,000 meters. And that's it. Oh, good. We match our answers there. That's always good. And there's a couple homework questions. You can try those.